Okay, I think we're all here. So everyone, welcome back. Hope you enjoyed the break. Now we're going to have one invited talk, and then we're going to have a very short 10-minute break before we have more contributed talks. So we're very pleased that Rafaël Bocquet is here, who's going to talk about strict Rezk completions of models of type theory.
Okay, thank you very much for the introduction. Right, so the motivation for this work or the intended application is that we want to do meta theory of type theories, which means we want to prove various properties of type theories and or properties of their models or syntax. Various kinds of properties we may be interested in, some that involve characterization of terms or types up to definitional qualities, so for instance, scancity or normalization, and then properties that involve characterization up to identification or up to homotopy, such as homotopy scancity, and we can also imagine some homotopy normalization results. Yeah, maybe another class of problems we may be interested in are things that involve multiple type theories or type theories and categorical models. So here the goal would be to establish various comparisons between these, and this can often be seen as some kind of coherence theorems. What's important is that type theory is quite strict language, and when we study models of type theory, we are studying some strict algebraic or more precisely general algebraic structure. Yeah, so for instance, you can say that models of type theory are categories with families, but what's important is that in this structure we have lots of strict equalities, and we may run into some coherence issues when we try to prove properties up to homotopy. So it seems that it would help to consider a notion of higher model of type theory, where we make more explicit or more directly available some of the homotypical structure that is here in the models of type theory. Oh. Share video. Okay. Yeah, sorry, let me continue. All right, so it seems useful to consider more general notion of model of type theory in which the homotypical information that is available in models of type theory is more directly available. So like the components of models of type theory are sets, and instead we want to have higher models for which the components are infinity groupoids. Okay, and we could imagine that this infinity groupoid of terms, the zero cells are terms in the model, and the one cells should be terms of identity type or coincide with terms of identity types, and so on for higher cells. And kind of the advantages of this point of view is that some of the statements of properties we're interested in are admit more natural statements using this language. So for instance, homotopy canicity becomes so the statement of homotopy canicity becomes the fact that this infinity groupoid of closed terms of a Boolean type is equivalent to the set with two elements, true or false, seen as an infinity groupoid. So some notions of higher models of type theory has been proposed based on some infinity categorical definitions. Yeah, I wanted to have some new line here. So there's a notion of infinity categories with families by Nikolai Krauss, and also some notion of infinity type theories by Nguyen and Uemura. But the idea in both cases is that where a category family is one category with additional structure, we instead use some infinity category with additional structure. Okay, a small problem with this is that, well, if we want to work with this, we have to work with infinity categories, and I guess it's more of a personal problem, but I find this a bit complicated, or I'm not enough familiar with the tools. But more importantly, when we switch from one categories to infinity categories on the type theoretic level, this more or less corresponds to a weakening of judgmental equality. And because in the end, we want to prove properties of strict models, if we want to use these infinity categorical models, we have to establish coherence theorems that compare between strict models and these higher models. And the coherence issues that are involved are quite hard. So yeah, so we can try to look for other options. Okay, and so the goals of this talk is that I will try to explain that sensible notion of higher model of type theory are cubical models, where the terminology is maybe a bit confusing because these are not the same thing as cubical sets model of type theory, but just ordinary models of type theory, but internally to cubical sets. And the idea is that by working internally to cubical sets, we can use the homotypical content of cubical sets to describe the infinity groupoids we are interested in. And we still then have an issue once we choose to use these cubical models that we need to compare strict models with some cubical models. And the solution for this is provided by this strict Rezk completion, which is a way to take a strict model and complete it complete it into a higher model that is univalent where univalent means the same as for univalent categories in homotopy type theory. Essentially, if you think of infinity groupoids, this will force the infinity groupoid of terms to be the one we want, where higher cells correspond to iterated identity types. And so that's more or less, this will be more or less the specification. And then I will try to explain how we can construct these strict Rezk completions in cubical sets. And the idea is that the same tools that are used to construct univalent inverses in cubical set models can also be used to construct univalent algebraic structures, so namely the strict Rezk completions. So if you try to make a list of what is needed for some applications, so as I mentioned, we want to define these infinity groupoids of types, terms, and other components of a syntax. Furthermore, we want to use a definition of infinity groupoid that is well behaved enough, in the sense that we are able to use it to perform some constructions. We are able to talk about families of infinity groupoids indexed, maybe over types or terms, things like that. Yeah, so essentially we want these infinity groupoids to be types in some nice enough model of homotopy type theory. Okay, and having this infinity groupoid is not enough for applications. We also want to have some additional structure. So at the very least, we want all type and term formers to extend to morphisms between these infinity groupoids. Maybe we need some additional coherence data. It's not clear at this point. But yeah, the hardest part is that we also want to have lots of strictness in this condition, because in the end, the goal is to prove properties of strict syntax, so probably to prove properties of some initial strict model. And so in order to use initiality, we want to have some model construction. So we want to construct new strict models from this data. And because we have lots of strictness in strict models, we also need to have the corresponding strict equalities at this level. And I guess this is the part where lots of coherence issues can come up. However, we can notice that this makes sense for models of Prot and other type theories, but we can ask more or less the same for models of other algebraic theories that have homotopical content, such as categories and nk categories for various n and k's, including maybe infinity categories, and in general, like maybe algebraic structures which have some kind of modal structure on their categories of models or something similar. Okay, and the point is that we can first try to look at what we can say for categories and then generalize for models of type theory, which are much more complicated. So if we just want to define these infinity groupoids, so we know how to, already know how to do this, maybe in multiple ways, but one of them is to use this weak modal structure constructed by Kapelkin and Lumsdain on the category of models of type theory. Okay, and then if we have some model M that is nice enough, so let's say cofibrant and fibrant, we can look at maps from this model that is freely generated by a context, a term, and type. Then maps into M correspond exactly to terms of any type in any context in M. But because we have some kind of modal structure, we actually have we can actually extend this to some infinity groupoids. And this will be quite well behaved, and you can use lots of tools from the modal structure, but we do not have enough definitional equalities for applications. Okay, so if we start thinking about models of type theory and start thinking about categories, one way to construct the data we want, so for a category, we essentially want to construct some infinity groupoid of objects that is the correct one with respect to the homotopy theory of categories. And one way to achieve this is to use Rezk completion of categories in HoTT. Okay, so here are the step. We start with a category in sets, so just an ordinary category. We can view it as a category in some model of HoTT. So here I use cubical sets. We can also use simplicial sets, I guess, or other cubical models. And to see it as a model in cubical sets, we view the category as a cubical category with discrete components, so with a cubical set of objects and cubical family of morphisms, but which are discrete as cubical sets. And discrete cubical sets are fibrant and zero truncated, so this indeed lives not only in cubical sets as a pre-shift opos, but also in cubical sets as a model of HoTT. And we know we can construct Rezk completions of categories in HoTT. So we can use this construction and apply it to our category, and we get a cubical category where now the infinity groupoids of object is the correct one with respect to the homotopy theory of categories. And furthermore, this new category is equivalent to the original category, so any property we are interested in can be transferred through this weak equivalence. So essentially, we want probably the same for models of type theory. So the question is, can we specify some kind of Rezk completion or generalization of the Rezk completion for models of type theory? And indeed, we can view any external model of type theory as a strict model in HoTT in the same way. But the issue is that we do not have any notion of non-strict model of type theory that can be expressed in HoTT. Okay, so the reason is that in the definition of model of type theory, we have lots of equations involving substitution. And if we remove the assumption that the components are H sets, then we need to add coherence data. And for the same reason as we run into trouble when trying to define semi-simplicial types, we observe that we would need to add some infinite amount of coherence data, and it's also quite hard to describe. So I guess it will be an open problem to give some definition of untruncated model of type theory in HoT. So one solution is to make all of the missing coherence data explicit, but this essentially amounts to the use of infinity categories instead of one categories as our notion of models of type theory. And so we can do that, and this probably works, but we still have some coherence issues as mentioned before. So the alternative is that if we are already living HoT, we might as well use some strict equalities. And so we still use models in which all of the required laws, substitution laws are strict, but we do not ask for any truncation of the components. Okay, and this can be, this makes sense in general in two-level type theory, but let's focus on cubical sets. And so cubical sets, and I'm using the Cartesian variant. Cubical sets are a model of two-level type theory, which means we have some outer layer, which is a model of extensional type theory, in which we have a notion of strict equality. And we have some inner layer with universes of fibrant sets that are univalent and that model homotopy type theory, and with a weaker notion of equality at this level. Okay, so we can use the definition of model of type theory in the internal language of cubical sets, and it is known that this is equivalent to overcharacterization of the notion of what is a cubical model. So we can either have models in the internal language, we can have models valued in cubical sets, which is, essentially almost by definition equivalent to the first characterization, but slightly different point of view. And we can change the place where we quantify over the cube category, and we get that cubical presheaves are also equivalent of, cubical presheaves of models are also equivalent to this notion of cubical model. And this works for any finite limit theory or essential algebraic theory. So in particular, the same holds for cubical categories. So once we start looking at cubical models, we want to restrict to cubical models which have fibrant components. So the reason is that we want to view these cubical models as higher models which have infinity groupoids as their components. And in cubical sets, the sets that can be seen as infinity groupoids are the fibrant sets. Right? And then we want to consider this univalence or completeness or saturation condition that a model is saturated if terms of the identity type in the model coincides with cubical paths between terms. So this is the same definition as for as the univalence condition for categories in HoT. Just the target is terms of the identity type instead of isomorphisms in a category. And it's actually usually better to consider this equivalent characterization using contractibility. Okay, and once we have these definitions, we can specify what would be a strict Rezk completion. And here I'm talking about strict Rezk completion because the Rezk completion of a category in HoT is a category where all of the laws are, given by identifications in HOT, but here all of the category laws and functor laws are strict equalities. Yeah, but I guess that Rezk's definition of complete Seagal space would be strict in this sense, so maybe the name is not the best, but I think it makes sense when comparing to Rezk completion in HOT. Okay, and we ask for a new category. So we start with category C. We want a new category C bar, such that this category C bar has fibrant components, so it can be seen as a so the components can be seen as infinity groupoids. The category C bar is saturated, and we also want I to be some kind of equivalence of categories, but because of but in the end, with the construction I have, we are only able to prove that I, after we move back to external categories, becomes a weak equivalence. But internally to cubical sets, it is not at least not a split weak equivalence, because the choice of lifts will not be stable under cubical operations. Okay, and the reason is that to compute the lifts, we have to decide some cofibrations, and cofibrations are only level-wise decidable in cubical sets. Okay, and then we can just use exactly the same definition for models of homotopy type theory. So I just replaced model by replaced category by model, and replaced the saturation condition by the appropriate definition. Okay, and so if we are able to perform the construction, then we can indeed get some of the applications that you're interested in. And I will try to explain why the same tools that are used to construct univalent universes in cubical set models can also be used to perform the construction. Okay, and so I'll say a few things about cubical set models. So there's been a lot of work by a lot of people, I guess lots of people in this audience, towards the construction of cubical set models, using the idea that we can axiomatize almost everything in the language of cubical sets, and then we have some tools that will construct univalent universes and prove that all type formers of HOT can be interpreted so that we have some fibrancy for various type formers. Okay, and the idea of axiomatization is that we assume we have a set called the interval with two distinguished endpoints. And then if we have any set X and we look at maps from n to X, this can be seen as n-dimensional cubes in X. And essentially what we want to do is specify what it means for a set X to be fibrant or trivially fibrant in such a way that this corresponds to like the usual external definitions of fibrancy and trivial fibrancy in cubical sets. And what's important for the specification of fibrancy and trivial fibrancy is that we have a notion of cofibrations, which is a sub-universe of universe of propositions, and assumed to be closed under some operations. And this provides a way to talk about partial n-dimensional cubes, or partial elements, which can be seen as cubes in X in which only some of the faces are given. For instance, a square where only 3 of the sides are specified. So I won't talk about the definition of fibration, but here we have a definition of trivially fibrant sets. And the idea is that we have this definition of extension structure. Having an extension structure on a set says that if we have any partial element of a set where the partiality is controlled by some cofibration, we can extend it to a total element. So for every cofibration and every element of X defined where the cofibration holds, we get an element of X such that when the cofibration holds, it reduces to this partial element of X. And essentially, this says that if you have any n-dimensional cubes where only parts of the cubes are even, we can complete it to a full n-dimensional cube. In particular, if we have 2 points, like the boundary of a one-dimensional cube, we can complete it to a line. And if we have some empty zero-dimensional cube, so no data at all, we can complete it to a point. Right. And so trivial fibrancy corresponds to contractibility. Yeah. So now I'm trying to get a candidate definition of how the street trace completion should be given. So normally we have a universal property for the Rezk completion that it is initial among saturated category with a functor from the base category. Usually in HOT, the preferred definition of the Rezk completion of a category is through the Yoneda embedding, so as some subcategory of some presheaf category. But this makes, so this is very specific to categories, and we cannot use the same definition for non-categorical algebraic structures. So instead, we try to start with the other definition of the Rezk completion, which is as some kind of higher inductive type or some kind of initial object somewhere. Okay, so for the street Rezk completion, this would be some quotient higher inductive type because we have at the same time some path constructors, but we want it to be strict, so we also have some strict equalities. Yeah, so I guess maybe the general semantics of this will not be completely clear. But in cubical sets, we would expect to have a definition that looks like this. C bar should be the initial category equipped with the following data, some functor from C to C bar, the saturation condition, which can be expressed as path constructors. And because we want to have something that is fibrant, we would also add constructors H-comp that corresponds to homogeneous fibrant replacement. And these are usually needed in the semantics of higher inductive types. So we can try to use this definition, but we don't know how to prove that the map I is a weak equivalence. So we are a bit stuck here. Fortunately, there is a solution. So it is observed in a paper by Cherubini, Cocan, and Hatzler that for some higher inductive type, we can omit the constructor, or we can omit the homogeneous fibrant replacement. In particular for the propositional truncation. And we have a following definition of the propositional truncation as the initial set equipped with a map from the original set into the propositional truncation, and with this family of extension structures. So extension structures correspond to contractibility. So this essentially says that whenever we have an element of the propositional truncation, then the propositional truncation is contractible, and this conditional contractibility is known to be equivalent to being a proposition. So this is essentially saying that we have a proposition, but thanks to the fact that we use extension structures and not the usual hot definition of contractibility, we are able to prove that this set is fibrant. And furthermore, this can already be seen as a special case of a strict Rezk completion. So essentially, we start with a set, and we want to see it as a proposition, and this corresponds to the modal structure on sets that presents propositions. And again, if you think of a set as a category, if you think of a proposition as a category where all home sets are contractible, then this is also a special case of Rezk completion for categories. And this means that we have the following candidate definition of strict Rezk completion for categories, which is essentially the same as this, but where we remove the homogeneous fibrant replacement and where we use extension structures to express the saturation condition. Okay, so it's freely generated by a functor I from C to C bar, and then this isomorphism extension structure, which says if we have an object, then the set of objects that are isomorphic to the first object is or has an extension structure, so is contractible. Okay, and I like to think that there are also other extension structures corresponding to every sort of the theory of categories, or every generating cofibration of the modal structure on categories. But for categories, we can actually omit these. If you look at E-categories instead of categories, then you would actually need to add these. So they're morally needed, but actually redundant in this case. But it's, yeah. Okay, and then for modals of HoT, we do exactly the same. We ask for a strict morphism into our candidate strict Rezk completion, and we add this identification extension structure. Whenever we have a term of any type in any context, then the set of terms that are identified to it has an extension structure. And we also kind of need something for types, but if we look at modals of HoT, and if you also assume that types are definitionally isomorphic to terms of the universe, then we can also meet this condition. Okay, so we have these candidate definitions, and then we want to check all of these. So saturation is built in, so there's nothing to do. So what has to be done is to prove that we have fibrant components and prove that the external functor is a weak, sorry, that I is some kind of a weak equivalence. Yeah, and I'll focus on the more difficult part, which is proving that the components are actually fibrant. But we can observe that these extension structures that you have are very similar to the equivalence extension property, which is used in constructions of cubical set models to prove fibrancy of the universe. So, okay, so this is some kind of equivalence formulation of univalence, where we say that for any type, the space of types that are equivalent to it is contractible. But when we express this using some extension structure, then we can derive fibrancy of the universe of fibrant types from this. So how do we do this? One way to do the construction is to factor it through this lemma. If we have some reflexive graph, so some diagram that looks like this, where we have vertices and edges that depend on pairs of vertices, and for every vertex there is some reflexive loop, so some edge from x to x. If we have a reflexive graph in cubical sets that satisfies two conditions that will be on the next slides, then the set of vertices is fibrant. Again, actually, the proof is just one line if you have the correct definitions. So what are these two conditions? One corresponds to these extension structures. So it says that we have an extension structure like this. So this is similar to the extension structures we have seen so far. And this is related to the notion of path object, because we have a reflexive graph, and then we had some condition that some of the maps are some kind of equivalence or trivial fibration in this case. Okay, and the other condition is that we have a coercion operation, which says that if we have a line of vertices, we can construct edges out of it. So if you have a line of vertices A and 2 points in the interval, we get an edge between the line evaluated at the two endpoints, such that in the reflexive case, it coincides with the reflexivity map of the reflexive graph. Okay, and then how can we prove fibrancy of the universe? It is by applying this lemma to the reflexive graph, where vertices are fibrant sets, edges are equivalences between fibrant sets for a suitable notion of equivalence. Okay, and then the first condition is exactly the equivalence extension property, which can be proven using the construction of glue types. And the second condition, the coercion operations, are derived using the fibrancy of vertices. Okay, so this lemma can be used to prove that a single cubical set, so this is a global cubical set, so it can be seen as an excellent cubical set. So it can be used to prove that a single cubical set is fibrant. But for instance, in the case of categories, we may want to prove that morphisms are fibrant when seen as a families over pairs of objects. So what we can do is generalize this to dependent reflexive graphs, so diagrams that look like this and commute. And then we can modify a bit the two conditions, and the result becomes that this map is a fibration, or if we view this as a dependent set over this set, it becomes a family of fibrant sets. Okay, so let's see how we can prove that the components of the strict rest completion of a category are fibrant. And the idea is to rely on the fact that not only categories have a model structure, but this model structure can be constructed as a cylindrical model structure, which means that we have very well-behaved path functors, which are right-tangent and so dual to cylinder functors. I guess if I start with path functors, this should be called a path model structure, maybe. Okay, it doesn't really matter. So for categories, the path functors can be constructed as categories of isomorphism in your base category. And once we have this data, we can construct diagrams that look like this, so that are instances of this diagram, where if we take any map, we get a diagram like this. So any map and any category X, or here I'm considering some candidate strict race completion X bar. And we get a diagram that looks like this. And then our lemma can be used to prove that the map on the right is a fibration. And for correct choices of I, we get that this map between sets are exactly projection from the set of objects to the unit set, projections from morphisms to the two endpoints, or the two source and target, and projections of equalities between morphisms into two parallel morphisms. So this would correspond to this, this map. Okay, and then we can check the condition. The homotopicality condition is exactly the isomorphism extension structure when we look at objects. When we look at morphisms or equalities between morphisms, these are the two other extension structures that were redundant in the okay, sorry. Yeah, so these are the two other extension structures that were redundant in this definition. Yeah, and then for the coercion operations, the idea is that we want to define it by induction on this component, because these are these vertices will be some component of the candidate strict race completion, and it has universal property, so we can do induction. So here we are under some interval binder, but in cubical set models, there is this property that the interval is tiny, and this permits induction under interval binders, essentially. Or a better way to actually prove this property is to use some universal property of lines in, here I use X, this should be X bar. And this was suggested by Christian Sattler, that we have this isomorphism or the characterization of the universal property of this. So lines in C bar are the same as applying the bar operation to to lines in C. Yeah. And you can use this to define the coercion operations by induction. Okay, and what about models of type theory? So unfortunately, they don't have a modal structure as far as we know. So there is this left semi-modal structure that was constructed by Kapulkin and Amsden, and I believe it should have a pseudo-cylindrical weak modal structure, where pseudo-cylindrical is a generalization of cylindrical, where instead of having a reflexive graph, we have a pseudo-reflexive graph, where so instead of M here, we have some new object of reflexive loops, and instead of requiring that the composition here is the identity, we require that the composition here is a trivial fibration. Okay, and this this structure is called weak Quillen cylinder by Simon-Henry. Yeah, and here I say should have, because I probably have not checked all of the properties, but just what was needed to construct the strict race completion. But yeah, I expect that yeah, this all works. And also for applications, having a weak modal structure is not quite enough. We actually, I mean, it's enough for some applications, but we want to use some notions of split weak equivalence instead of weak equivalence. So we want to know not only the mere existence of lifts, but we actually want to be able to construct lifts when we have a weak equivalence or a vibration or a trivial vibration. So we want to use something more algebraic than just model structure or weak model structure. Yeah, so I guess there's some. I guess there is some notion of algebraic weak model structure that has to be studied and hasn't yet been studied, as far as I know. Okay, and then once we have these pseudo path functors, we can use we can do the same as in the case of categories, but for a generalization of the lemma for pseudo-reflexive graphs instead of reflexive graphs. So we look at diagrams that look like this. Yeah, I have not written the exact condition, but we still need some homotopicality and condition and some coercion operations, but they have to be weakened a bit. So for the homotopicality, we need that not only pi1 is trivial vibration, but also the composition pi e with pi1 is a trivial vibration. And for coercions, we need to replace them by weak coercion operations, where the condition in the reflexive case is given by an element of these sets. Okay. Yeah. So I guess so far the main application of this construction is that this provides a new proof of homotopy identity for homotopy type theory. Yeah, and I've not given any details here, but once we have this construction, we can essentially do the same as for a proof of ordinary canonicity for Martin-Love type theory, and just replace the syntax of HOT by its strict trace completion, and do the exact same kind of construction that is used to prove usual canonicity, and we get a proof of homotopy canonicity, working in cubical sets. Okay, and then there are some questions. I guess one question is that I've not written here is what is the most general construction you can do. So I guess we want to have a construction for any pseudo-cylindrical weak modal structure or something like this. Yeah, another question is, can we relate precisely this construction to the homotopy theory of our original category? So we can see the strict trace completion as some kind of vibrant replacement in cubical models. So then we want to relate some probably some kind of weak modal structure here to our weak modal structure that we have here. And I should say that seeing this as a vibrant replacement was suggested to me by Christian Sattler. And the other question is that is needed for some applications is, can we add some even more the definitional qualities? So can we require that the extension structures that we add are stable under substitutions? And that's needed for applications to homotopy normalization.
Thank you very much. I think we have time for one or two quick questions. Anyone? Okay, I'll do a quick one then. Oh, Fred, yes. Go ahead.
Yeah, thank you. So you had this new notion of higher inductive types with the extension property. Can you justify this somehow? Is this easily constructible in the models, or because it doesn't quite follow the standard schemas of higher inductive types?
I mean, it is some quotient inductive type. I mean, so this yeah, like something like this.
Yeah.
So it's not a higher inductive type. I mean, you have lots of strict equalities in categories and in functors, and also here as well.
Yeah. So that's the one I'm wondering about.
But I mean, the existence of C bar is is okay. I mean, this is the initial algebra for some infinitary essential algebraic theory, and actually sub-finitary. So the only infinitary part is quantification over propositions, but cofibrations.
Right, but you're using the fact that you're in a two-level type theory to state this.
Yes,
right?
yeah. So this is in a two-level type theory.
Yeah.
I mean, we don't have any path constructor on the
strict ones.
On the point constructors and strict equalities.
Yeah,
I guess.
Yeah, thanks.
Any others? Yes.
I just wondered your second point. I was a little bit confused if you were saying this is a theorem or a conjecture about the second bullet. That it is a fibrant replacement?
I mean, it can be seen as a fibrant replacement, but it's not clear. I'm not sure whether it's part of a weak modal structure, but it's.
Okay.
And I guess I'm not. But
I guess so it's a fibrant replacement in some weaker sense than I have a model structure and blah blah blah. But maybe you have a fibration category, and this can be seen as.
Yeah. So it's so essentially, this is so here, like for some when you define fibrations, you say that you want to have a solution to every lifting problem, and here you say that the space or the set of solutions to every lifting problem should have an extension structure. Mm-hmm. But I believe it can also be seen as the usual kind of fibration by just changing the cofibrations, but I've not verified this.
Okay, my second question was whether when you say it's a fibration in some purported model structure or something weaker, whether you know if that presents the same thing as the notion that you started out with of infinity type theory. Meaning, are the things that you're generating here, is it general enough to cover all infinity type theories?
Yeah, I mean, I guess that's the question. So I have not verified this. I expect that. So it's not a theorem. Yeah, so I know Christian Sattler has verified a bit more than me, and maybe that's already a theorem for him, but I don't know.
Okay, then let's have a 5-minute break and let's thank Rafaël again.